I just will say again that we begin with Professor Grobler from Northwest University, South Africa. He will present us the talk entitled Remarks on a Generalization of Doob's Optional Sampling Theorem. Professor Grobler, it will be for you in 2 minutes, and you have 30 minutes. Thank you.
Thank you very much. I'd like to thank the organizers for giving me this chance to present the paper. And I must confess to you that I'm not teaching anymore, so I have no experience of doing this in this manner. So if things go wrong, just have patience with me. I will now share my screen with the talk, and then I think I will start in a minute or so. Okay, so I will start. You see there is the title of my talk, as it was mentioned. And oh, let me just for a moment see. Why doesn't it want to? Right. Let me say something about Doob sampling theorem in general. Consider a process xt in which xt represents the fortune at time t of a gambler, and he is supposed to play continuously, if that is possible, and he is competing in a fair game. The question is, can he hope to improve his expected fortune by judiciously choosing the time to quit? If he can only rely on information obtained in the past, because he's not clairvoyant, the answer should be negative. Now, a model for such a fair game is a so-called martingale process. And loosely speaking, Doob's theorem states that the martingale remains a martingale if one plays around with the stopping times. This remains true even if the game is not fair, but is loaded in favor, for instance, of a casino. Changing the stopping times does not change this fact. Discussing this theorem gives one a good opportunity to illustrate many ideas and methods used in generalizing the theory of stochastic processes and probability theory to abstract Riesz space theory. So what we consider is a Dedekind complete Riesz space E with elements x, y, etc., called the stochastic variables, and with a weak order unit E. The Boolean algebra of all order projections will be denoted by P and its elements by math, blackboard, bold, P, Q, etc. And they are called the events. We assume that there exists a positive order continuous projection F on E that maps order units onto order units, and we denote its range by run F. By script F, and we denote it by script F, and script F is a Dedekind complete sublattice of E. It is this mapping is called a conditional expectation on E, and we may assume that this conditional expectation maps the order unit onto the order unit. Now, the set of all order-bounded band-preserving operators called orthomorphisms will be noted by ort E like that. The elements of ort E are denoted by S, T, etc. Good. Suppose we have an interval J in the positive reals, and we considered any function which maps a T8 from J onto an element xt in E. And such a function is called a stochastic process in E. Now, a filtration in E is a family of conditional expectations with the property that Ft is equal to Fs for all s less than t. The corresponding ranges then satisfy the condition that Fs is contained in Ft for s less than t. The Boolean algebra of order projections in FT will be noted by PT. The stochastic process is said to be adapted to the filtration FT if the element xt belongs to FT for all t in J. The stochastic process xt adapted to the filtration FT is called a submartingale whenever fs of xt is larger than or equal to xs for all s less than t, and a martingale if equality holds. Now, for an element in the set of orthomorphisms, we put S equal to SE. This is an element of E, therefore. And we let STL be the projection onto the band generated by the band on which TE is larger than S. That is, we look at the element TE minus S plus, and we look at the band generated by the element TE minus S plus, and we say that is the band where TE is larger than S, and the projection onto the band will be denoted by that. In the same way, we let EL be STEL, and that is again the projection onto the band generated by TE minus S. That is the band on which S is less than or equal to TE. Now, this is an increasing left continuous system called the left continuous spectral system of S. These spectral elements, ET, they are used in Frontal's spectral theorem to prove the theorem. In a similar way, we can get the projection onto the disjoint complement of that band, and those are called ERT, and that is an increasing right continuous system called the right continuous spectral system of S. S, the orthomorphism S, is called a stopping time for the filtration if the right continuous spectrum is adapted to the filtration. So this is also a stochastic process, and if it is adapted to the filtration, we call it a stopping time. On the other hand, if the left continuous spectrum is adapted to the filtration, we call S an optional time. And we note that every stopping time is an optional time. Now, this is just a technical point. We denote the universal completion of E by EU, and the space E is called the F universally complete in EU. Whenever we have that, if X alpha is upwards directed in E, and if X alpha is bounded in the universal completion, then X alpha is upwards directed to an element. Its supremum exists in E. We shall henceforth assume that E is F universally complete in EU. This is because we wanted to apply a theorem by Bruce Watson that if E is an order closed subspace, if G is an order closed subspace of E, and F is contained in G, then there exists a unique conditional expectation Fg on E with range G, and it commutes with F. This is a very important thing that one has to have this theorem. Otherwise, one cannot do this theory. And we shall use the fact, and this is important for later on, that an element is the conditional expectation of an Z is the conditional expectation onto G of X, if and only if we have F of PZ is F of PX for all projections P in the set of projections on G. Think of F as an integral and P as a set. Then this tells you that the integral over P of Z must be the integral over P of X for all P in PG. Then Z is the conditional expectation of X. Then just something else. If FT is a filtration on E, then we can form a new filtration FT plus by taking the intersection of all Fs for S larger than T. This is the filtration called the right, or rather, the filtration is called right continuous if Ft plus is equal to Ft for all P in J. There exists then, by Bruce's theorem, a unique conditional expectation ft plus from E onto this, satisfying this commutative relation. The set of all order projections in the space ft plus will be noted by pt plus and is called the events immediately after t. The set of events immediately prior to the stopping time s is given by this this set of projections that you see there. It is really the set of all projections generated by the projections of all FTs prior or less than or equal to Fs together with the spectral projections of S. Those are the right continuous spectral projections of S. And PS is a complete Boolean subalgebra of P. And with all those P's, we can associate, of course, a lot of components of E, and we call that CS. We denote the order closed Riesz subspace of E generated by Fs. By Fs, we denote the order closed Riesz subspace of E generated by CS, by all those components. Denote by Fs the unique conditional expectation that maps E onto Fs, which again exists by Bruce's theorem. And it has this property. Now, the set of events determined immediately after the optional time S is given by a similar expression where we simply replace the right spectral projection by the left spectral projections. Okay. That is where we were. Yeah. Okay. Let S be an optional time for the filtration. As before, we denote those components by that. We define a vector measure on the intervals ST by defining the measure of an interval left closed, right open, by the difference of the two components. This defines a sigma additive vector valued measure on the algebra of all finite units of disjoint subintervals of the form ST in J that can be extended to a sigma additive measure on the sigma algebra of all Borel subsets of J. Now, for the partition pi written there of J, we define L to be the Riesz space of all right continuous simple processes of this form. So it's clear what is meant by that. Chi S denotes the indicator function of the set S. With pointwise ordering, L is a Riesz subspace of the Dedekind complete Riesz space E to the J of all sigma valued functions mapping J into E. And for such an element of E, we define an operator IS of such an element to be the sum that you see the XTI, the measure of that function. Now you see it's a vector measure defined by an and this is a component of E, of course. So this is a multiplication in the F algebra of all components. Well, it is also the projection applied to XT. Now, if you look at this definition, then we have the following proposition. This operator from L to E has the following property: is positive linear. It is sigma order continuous, which means that if XNTL is in L and is downwards directed to 0, for each T, fixed T, then IS of XNT is downwards directed to 0. And IS, defined in that way, is a lattice homomorphism. The operator IS is therefore a positive vector valued Daniell integral on L. We denote by LS the Riesz space of all Daniell S summable vector valued functions. This extended integral is a Riesz homomorphism. So that is a special property that this operator, this Daniell integral with reference to those measures. Okay. Now, an adapted, just to say which functions are S-summable for this Donnell integral, just as an example, any adapted left continuous process xt that is bounded by a S-summable vector valued function x is S-summable. In particular, if you have a process in which the absolute value of xt is less than or equal to m times e for some fixed m, then this is an S-summable function for this Donnell integral. And then we have the definition of stopped element. For an element x in LS, we define xs as is of xt. Now we have the following proposition. If xnt is a sequence in LS that is UO convergent to xt in LS at each point of t, then this is UO convergent to xs. So this, you recognize this as a kind of Lebesgue theorem. Okay. Now the next thing that we have to define is the backward submartingales, also called the reverse submartingales. Suppose that Fn is a decreasing sequence of Dirichlet completeness subspaces satisfying the n plus first one is contained in the nth one, and that Fn is the range of a conditional expectation Fn from E to Fn, satisfying this condition. So it is just the reverse condition that you have for a sub martingale, but it is going backwards. The process is then called a backward submartingale whenever Fn plus 1 of xn is larger than or equal to xn plus 1. Now, we assume that all these Fn's, these subspaces, are contains F, and F is the range of our fixed conditional expectation. And so we have that F is contained in that. And what we do now is we add F simply to this downward decreasing sequence. And then we have a chain which has a least element or a last element. The conditional expectation F has the property that for each n we have that is true, and therefore F of xn is larger than F of xn plus n plus 1. That means the sequence Fn is a decreasing sequence. It's also easy to show by induction that Fn x1 is larger than or equal to xn for all n. Now, we now have two convergence theorems, one for backwards submartingales and one for martingales. Both were proven by Riesz, Labuschagne, Martelly-Korostensi, and the Leibkuhn-Labuschagne. And I think we are the one for I think Wenchi was also involved in this work. In any case, here's the theorem. Suppose you have a backward submartingale with a last element or first element. I don't know what to say. If the sequence is bounded below in this way, then the sequence xn is ordered convergence to an element of E. We don't say what the element is, but we know then that this is order convergence. This is for backward submartingales. The same for submartingales. If you have a submartingale and the sequence has a last element x infinity, then it is order convergent to some element of E. This is not exactly the way in which they formulated it, but it can easily be derived from their convergence theorems. And here now is the optional sampling theorem. It says, if you have a right unbounded order continuous submartingale and S and T are two optional times with S less than or equal to T, and they are optional times for the filtration Ft, then if either T is bounded or if Xt has a last element, we have that conditional expectation of xt is larger than or equal to the element xs. And if s and t are stopping times, they are of course also optional times. So this also holds if s and t are stopping times, but in the case where they are stopping times, then fs plus is equal to fs. So one can replace that s plus by s. So you see, what happens here is that the submartingale property still holds, even if you change the s and the t's by stopping times s and t. So this tells you that you can fiddle around with the stopping times, but the submartingale stays a submartingale. And if this was a martingale, then you will have equality. So then the martingale stays a martingale. And I'm going to go through the proof quickly, because it is interesting for me. Well, the first thing that we do is we discretize the problem. In that, we take for Sn and Tn, we take step elements which converges to S and to T. And this is by Freudenthal's theorem. So we take typically the Freudenthal step elements there, and we can choose them since S is a bounded stopping time and therefore T less than S also bounded. We can take them downwards directed. So downwards directed stopping elements such that Sn is downwards directed to S and Tn is downwards directed to T. And Sn and Tn are stopping times for this filtration. That and for this finite submartingale that you get in this case. Okay, and now we can apply Doob's sampling theorem for the discrete case. And we have that f of Sn applied to xtn is larger than or equal to x of Sn. And this discrete case of the theorem was proven by Labuschagne, Wenchi Kuhl, and Koenraad and Bruce Watson. So we simply apply that discrete case. Now, for every p in the set of projections Psn, we therefore have that fp and xtn. F is fSnp, because p belongs to that, then p is equal to fsp. So we can replace the p by fSnp. But then we can also commute, and we have f of fp, fSnp, and then we apply that inequality, and we get it is rather than equal to f of fpsn. Okay, this is the first inequality that we get, and PS plus is the intersection of all the PSNs. That was proved in a paper about stopping times that I wrote. And therefore, by 0.4, we have that FPPN is larger than FPSN, that it holds for all P in PFS plus. Because it holds for all P's in PSN, and this is the intersection of all of them. So for every P in PSN, this also holds. And this is a very important inequality that we will use later on. Now, if S is a stopping time, we have that since S is less than S, PS is contained in PSN, and so this inequality also holds for all P in PS. Because PSN is contained in all the PSNs, so it is also contained in that, and so the same inequality holds for all P in PS. So we have this inequality for all P in PS plus, and also for all P in PS, if S is a stopping time. Good. Now, applying these arguments, which we apply to S and T, or T and S, what was that? S less than or equal to T, we now apply to Sn plus 1 and Sn. And we get this inequality as we got it before for all n, which implies that this is a backward submartingale. And so fSn is a decreasing sequence, and using the definition of xn, we have that f of fxn is larger than or equal to fxa for all n. And now we have that the backward submartingale is bounded below in a certain in the sense required to apply the convergence theorem. And what it says there, therefore, is that the sequence xSn is order convergent to some element of E. And the same argument holds for the Tn's. And so we also have that x of Tn is order convergent to some element of the space. But we don't know what the limit is, and we are soon going to find out. Note that x of Sn is equal to the integral with reference to the stopping time s of xn, where xnt is defined by this. So this is a very nice duality kind of, because what is xsn? Xsn is really the integral over Sn of xt. And so the Sn changed to S, but the xt changed to xn. So one just has to write this down, then you immediately see that this is true. And the same is true for the t's. And now, here we are. So xsn, which is order convergent, can be written as the integral of this this sequence of functions, and the same for xtn. Now, what we're going to do is to show that this sequence of functions converges, and then we apply Lebesgue, and it goes like this. By assumption, this is UO right continuous, and this implies that this is UO convergent to xt for every t. Now, take any k in n as a constant process. It is Daniell integrable, and xn infimum ke converges order pointwise to x infimum t, because the xn converges pointwise for each t to xt. So this converges to that. And we can apply, therefore, Lebesgue's dominated convergence theorem. So we get that the integral of that converges to the integral of that with reference to the measure induced by S. So that is true. That converges to ES. Yeah, that, sorry, converges to that. But now comes the fact that IS is a Riesz homomorphism. So IS of that is ISXN infimum ISKE, and that is equal to ISX infimum KE. And the similar holds for the limit. So what does this say? This says that that converges in order to that for each fixed K. And that means that the ISXN, which is equal to XSN, converges UO to that integral, which is equal to XS. So here in the other slide, we had that the sequence XSN and XTN converges in order, but we didn't know what the limit was. But now we see that they convergence UO to XS and to XT. So we get this result. So the limit can be determined by using these properties of the integral. Okay, but then if I take the limit as n goes to infinity in the equality 0.5, let me just get it for you. There it is. Now let n tend to infinity. In that we have that xtn goes to xt, xsn goes to xs, and we get the inequality with the xtn replaced by xt and the xsn replaced by xs. That is so. And therefore, we have for each f that f of fs plus xt, which is fp of that, and then I apply the inequality there, which I have there. So reading it from this side to that side, we see that by the defining the defining inequality or equality for what is the conditional expectation. This tells us, since it holds for all p in that the conditional expectation of that is equal to xs. So the integral of that function, and you can get the p, you should look at the last two. The integral over the set t of that function is larger than the integral over p of that function. That means the conditional expectation, that is the conditional expectation of that, and you get this inequality. So this proves the theorem if f, s, and t are bounded optional times. Now, my time is almost up. I think I have 3 minutes left. This was the case where the s and t are bounded stopping times. So the next that we want to prove, or the next part of the theorem, we have to prove it when s and t are not stopping times, but where the submartingale has a last element. And in that case, we follow more or less the same idea. Instead of those SNs, which were in the first part, Freudenthal step elements that converged to S, we now define Sn to be S infimum Ni, and Tn by that. And then we have that Sn is has S as a supremum, and Tn has T as a supremum. And then these things are now bounded stopping times. And therefore, I apply the first part of the theorem to these bounded stopping times, and we get this inequality. My time is now up, but it is then easy following the same kind of arguments. Again, we have this interchange between xsn and xn. We have, but now the function xn is defined like this. We define xnt to be xt on the interval a to n. So the first part of the n, and for larger part, we keep xn constant. So it stays constant. And if you calculate the integral over s of this function, then you find it is exactly xsn. Okay, and the same if you integrate over with a measure of t, we also get that. And therefore, I can again derive these inequalities from the fact that they hold for each xn, and I derive finally at the final inequality, which is the Doob's optional theorem that we wanted to prove. So thank you, Mr. Chairman. I think I'm just perhaps in time.
Thank you. Thank you very much, Professor Grobler. Are there any questions? So,
have you considered doing the continuous time version of AMART?
No, I have not. I've seen that you were working on that, but I haven't looked at AMRs. No. Perhaps something that we could look at. Okay, so there I can see you again.
I have a general question.
Yes?
You have an important contribution on this area by studying continuous process. And many results, many theorems has been generalized. My question is there something new about the classical theory or something like that?
Yes, this is a good question. My own view on this is that doing it in this abstract sense sometimes gives you some insights into the classical case, which just is not clear in the classical case because it is something obvious. For instance, this proof that I just gave you, where we define the stopping time. In the classical case, it is so simple to define it. It is just a composure of two functions. And if one of the functions is continuous and the other one converges pointwise, then you have this whole theory. While in this case, this shows you something about the structure of things. Another remark that I had is you often find that people in probability theory make a distinction between a stochastic variable and a function. And in our case, we don't have a distinction between the elements and other elements in the space. This tells you that probability theory people, when they talk about the stochastic process, they really talk about equivalence classes of functions. And what happens if you do the theory as we do it is many questions about almost true, etc. For instance, when you look at paths of processes and things like that, then the whole question of almost everywhere disappears because we don't have the concept of almost everywhere. We already work with the class of functions in their case. So there are insights like that. But to get new theorems, I mean, this hasn't happened yet. Sorry.
Thank you.
I have a question.
Yes.
You're working in the universally completion. Why? I think that you need a sort of completion. What you think about if we replace the universally completion by the Dedekind completion?
Well, you see, in any case, our spaces are Dedekind complete. So the reason for using the universal completion is really kind of a technical reason, which tells you that if you look at the space and the space is F universally complete, as we do, then it means that the domain of your of the conditional expectation, its domain has properties which the space L1 has. And if you look in probability theory, you will find that people work with conditional expectations defined on L1. And there are properties of L1 that one needs, and those properties can be used if one makes this assumption. This was really found by Bruce Watson and Konrad Loewe-Skagny. They defined it for the first time, and it the thing is really that guarantees you that conditional expectations exist, mapping the space onto certain subspaces, and that is indispensable. I don't know if Bruce would want to comment on this.
Thank you.
Is there someone else who wants to
Yes,
ask a question?
you need you need the extra structure of the maximal domain to extract some of the properties used to build stochastic processes and conditional expectation operators. That's where this type of completion comes in. And obviously it is the resulting space is larger than your Dedekind completion. So thank you.
Other questions? So let's thank the speaker again. And we will be back in 10 minutes with Professor Bas Lemax. It will be in 10 minutes. Thank you.